This is what we call the fundamental equation of motion. Whatever the system that you shall be having, whether 4 degrees of freedom, whether infinite degree of freedom, this is the fundamental equation of motion. At any one time, either of all these are acting together, or depending with the condition, one of the components might collapse, or we might eliminate. Okay? And as you can see, we are saying Ft, the externally applied force, is equals to Ku C U prime, U double, and the M. If you look at this equation carefully, this is a second order ordinary differential equation, whose solution now will give us the response of the dynamic system. And this is all what we'll be doing in this course. We shall be solving this equation for different type of system, different kind of degrees of freedom, and different kind of externally applied loads. Okay, so that the ODE based on the force, external force, we may have free vibration. If you assume that we have free vibration, then there is no external applied force. So you may ask yourself, how does the motion occur? So the motion occurs as a result of the external condition. I mean, the initial condition, sorry. So it's like the example I was given, or even, let me use a structural system instead of just giving a example. So the system that we have talked over, this is our rigid frame. And then we applied, let's say we applied a load. We applied a load initially, a displacement, we applied a displacement. So we pulled this structure, that was the initial resting position. I mean, that was our initiation of our motion. We applied an initial displacement here, U naught. Okay, so we displaced with a certain margin, then we release. If we release and allow the motion to continue, then it means that's a free vibration. The motion was initiated by initial condition. Okay, so we still have to put this one equals to 0. So even if it was a force that was applied, it was applied during the initiation of the motion, and from that point, the motion continued without any extra force or load applied. The force we may have here, we may use harmonic excitation. Remember, we said harmonic load or harmonic force is when it's periodic, that is, it's repetitive in nature, and the motion itself, the nature itself can be described using a sinusoidal function. Or we can have forced random excitation, like the impact wave, like the earthquake wave. Okay? So you see, already we have seen different scenarios how this external force can change. And we can also say, if the condition now of our system, if there is no damping, this one can collapse to 0. Of course, this would be an ideal scenario. And if there is free vibration, so this will become 0. So you only have Ku plus M U double dot. And as you can see here now, we have reduced our ODE to a homogeneous ODE. So that now you will start one thinking. For the people who are saying the mathematics you study, I will never use them. Now here you're going to use ODE. And the assumption is in this class that if you come across those equations, it's that because you already studied ODE and PPE, partial differential equations, it's already, you just need to refresh in your mind. You don't have to remember everything. But if you understood during that time, you just need to refresh. So what will be happening here is that for our equations, we already know the solution, the procedures for solving that. So just be moving quickly to the solution. Okay. Good. So we have seen how to come up or where the fundamental equation of motion gets its different components, the component of the equation. And even the coefficient, you can be able to explain what is that, what is C, Y, M, what is this F. And of course, now we can move ahead and start solving this equation. And we can start solving with the first case, free and damped single degree of freedom system. And this was the core of our topic for, or our discussion for today. All right. Now, in this case, we are saying for the free and damped vibration, free undamped. So no external excitation, no external force, no damping. So that means this equation, this is our fundamental equation, Ft is equal to 0, and C U d over dt is equal to 0. So you're only left with the component of K and of M, and this side is 0. So we end up having this equation. Here's what I was saying, equation 5 is a second order linear homogeneous ordinary differential equation. And in this case now we say from ODE, we know that the typical or the trial solution for this equation, we have 3 of them. One is when we have A cos omega t, B sin omega t, and also the superposition of the 2. And the coefficient A and B will depend with the initiation of motion. Omega, we call it, is a physical characteristic of the system. And what is this physical characteristic? When our motion is moving to and fro, when our structure is vibrating, there's what we call the vibration. We call the frequency of vibration. So this physical quantity, omega, is called the natural or the angular vibration. The angular vibration, we are also going to see the linear, the angular frequency, we are then going to see from angular frequency how we get the linear frequency. Okay, so omega, and is expressed in rads per second. Does it mean that damping in a structure is caused by external forces only? No. We give the different levels of damping that can occur. We talked of the external. We talked of the, if you remember this definition, we talked of the viscous damping. This is the internal because of the material property. And this is the one that we said we are going to concentrate ourselves with, the viscous damping as a result of the material characteristic, the friction between the different layers. Okay. Frictional damping, we said this is the friction, the resistance between the different parts of the structure, or even drag between feet or a structure. At the external, we say that these are the external forces that can cause or contribute to the increasing damping. But for us, we are limiting ourselves with the material characteristic. Of course, you may ask, why not consider the external things? We are trying to develop from basic principle, the fundamental, right? And you see, if we bring in so many parameters, so very different parameters, you may get confused at this stage. And again, the other thing is that because the material we can control, you know, we can study and understand the material. We already know viscous damping, the behavior between material characteristic is that the force is directly proportional to the velocity. But this might not be so if we are talking of the external cause of damping. So for our case here, for a start, we are limiting ourselves to viscous damping so that we can employ these very good relations. Force is direct proportional to velocity. Yeah, I can see, Humphreys, you're saying you should have told us last week to start. Oh, sorry for that. I thought to start brushing up on ODE. Yeah, good students should read ahead of the teacher, not necessarily using the note. But anyway, for sure you need to brush up. I remember, oh yeah, like last semester I told you to brush up on the matrices. So you need a little bit of ODE. I don't know, maybe slightly PDE, but ODE for sure. Okay. So for that case, where was I? Yeah, I was explaining that the damping is not only caused by external, and in this case, we are actually considering the internal damping because of the material behavior, and for the others, external damping, we hold it at a constant for now. Now, so you see, from our equation 5, and we have now the trial solution 6, 7, and 8. So if you can substitute equation 6 into equation 5, of course, the M here. So to do that, it means you have to differentiate twice. Yeah. This class is very easy because now this is mathematics that you already done. So if you differentiate equation 6 twice, you're going to end up with negative M omega squared And this equation already is substituted in this expression 6 is substituted in equation 5, and then common terms, we have rearranged and brought the common terms together so that we have equation 9. And this is the equation that is to be satisfied. It will be satisfied at any time. So what are we saying? There is, I think in mathematics here, you might have come across this term, where we talk of for non-trivial solution. For non-trivial solution. So this is the same case that we are saying here. For the equation, remember, for a motion to occur, it means, because we are saying these two components, this component in brackets times this, n cos omega t is equals to 0. It means either one of them have to be 0 at any one time for the equation to hold true. But for that to happen, then a cos omega t can be 0 at one time, but not at all time, because if it's at all time, then the motion dies. Because as you can see, this is the sinusoid. This is the motion where the wave is, the expression for the wave. So it means for all cases, for this equation to hold at all time, this factor in parentheses is the one have to be 0 at all times. So what are we saying? We are trying to get an expression for the unknown. Remember, in this case, the M is known, U is known from its displacement, K is known. But here, because of when we are getting our solution, we know the trial solution, there is a quantity omega that have come into play, the angular frequency. We need to know or to get the expression of the angular frequency. So you're saying now we equate whatever is in the bracket to equal to 0. If you equate that equals to 0, you're going to get omega squared, there's that, equation 10. And the square root of that is what we get it as a circular or angular natural frequency of the system. And the units are radian per second, the positive quantity. Again, of course, now equation 12 and 13, these are just different ways that we can express this expression. Because we already know that weight is equal to mass times acceleration due to gravity. So that gives equation 12. And again, at the same time, you know, weight divided by, this is from this expression, F is equals to K, K times displacement from the Hooke's law. Is it? So you know that displacement, maybe I should use, let me use what? Let me use this so that you're not confused. Capital displacement. So it means the capital delta is equals to F of K. Okay, and this is what we are saying. The static displacement, static, not dynamic, static displacement, you know, from Hooke's law. Static displacement is equal to F over K, or the weight of K. And this is what we replace with it here. So this quantity is very useful. We are calling it static displacement. This is the displacement of the spring due to the weight, instead of weight. So all these are just different expressions, how we can express our angular, circular, or angular natural frequency. Now, equation 8 is our solution. Equation 8 is our solution. 6, 7, 8 are typical solutions. Now we have used equation 6 to get the angular displacement. You can try also using equation 7 to get angular frequency. Now we are saying, now using equation 8, we can differentiate once so that we can get what is the velocity. Yeah, saying the velocity is equal to, if you differentiate this, you are going to get equation 14. And the constant of integration, A and B, can be determined from the unknown, from the known initial condition. Remember, for free vibration, our motion initiates as a result of the initial condition. And this is what is known. At time t is equals to 0, the initial displacement is known, or initial velocity is given. So initial displacement, u is equals to u naught, and the velocity, u line, u dot naught is equals to v naught. So we can be able now to obtain the coefficient A and B. So there's a bit of mathematics here that you really need to work them out so that at least they can get into your hands. So the solution of now our initial condition, or the solution of the ODE from initial condition constitutes what we call the initial value problem. That is, if you are solving an ordinary, or if you are solving not just an ordinary, if you are solving a differential equation, whether ordinary or partial. If you are using, if the solution you are solving from the initial condition, we call it IVB. Now, last semester, we were solving PDE. If you can remember the first presentation, the first few slides, we talked of the last semester, we talked of what is this finite element? What is this complex analytical expression that we are trying to break it up down so that we can use finite element method? And I remember I gave an expression now, PDE, there, and how we break it down. And those PDE, we said we might not be able to solve unless we bring the boundary condition. So for our case here, last semester when we were solving from the known boundary condition, that's what we refer to as boundary value problem. Okay. Then, sorry for that, there's a call coming here. And well, sorry for distraction. Good. So we are solving from the initial boundary condition. So like the initial, we already told that the initial displacement, u, at time t is equal to 0, u is equal to u naught, and the velocity is equal to v naught. So you can just substitute, like for time equals to 0 in the equation 14, you can be able to get what is the velocity. And from equation either 6 or 7, you can get what is the displacement. Because our equation of motion, equation 5, what is unknown is, it's like if you take it as x, this is like, find the value of x. It's like we are saying find the value of u. That's solving. That's what we are talking about in this equation. So the concept of integration, we said you substitute the initial condition in equation 8 or even 9 and equation 14. Equation 8 will help you. Equation 8 will help you to get the displacement, and equation 14 will help you to get the velocity. Okay. So that now you have what is A. A is u naught and B is v naught over omega. Therefore, equation 8, which was the proportion of the two solutions, is as shown in this expression. And as you can see again, this is an expression on an equation expressed. Equation 16 is an equation expressed using cosines and sine function, or is a sinusoidal function. So we talk of a harmonic motion. So our solution, the displacement u, is a harmonic motion. All right. Levi-Rook is saying that you are floating all the way. Why should you float? Yeah. Oh, if you want to sink, you need to take a pen and a pencil, and then you solve this. You solve with us, because I've already solved for you. It's just a matter of working out to see whether you can get these solutions. Okay. So this is a matter of solution for differential equations, ordinary differential equations. Okay. All right. So equation 16 is harmonic, and it's periodic and harmonic. And we are saying this typical kind of functions, they have a period as 2 pi. Okay. The period is the omega tau is equal to 2 pi. That is, we are taking the period omega capital T to be equal to 2 pi. Remember, you have already gotten the expression for angular frequency. Now you are moving to expression for period. Because this is about waves. This is about first year physics, waves. So we want to, for a wave, it's a kind of, we have a motion, we have established that our solution is expressed using a sinusoidal wave. And therefore, this wave have got some parameter. The characteristic of the wave. We need to know the period, the wavelength, and the amplitude and the frequency. This is what we are observing from. So you're saying the omega t, this component here, yeah, this component here, because the component here for omega t, for any wave, if it's a sinusoidal wave cos beta t, this is the component that gives you the period. We are saying this omega t, of course, we are just making this to be capital T to be the period. The whole of this t is equals to 2 pi, because there's a sinusoidal wave. You know the characteristic of sinusoidal wave. So the period is given out by 2 pi over omega. So equation 17, this is the undamped natural period, and the unit are in seconds. So the undamped natural period for an undamped single degree of freedom system. I'm going to look at this question that you're asking, Gabriel. Could you say that the natural frequency is a representation of how the elasticity of the object is interacting with the gravitational pull for the free and damped system? I'm trying to look at your thought to see what is it that you want to say. But if you look at just these expressions, I'm trying now to paraphrase maybe whatever you have stated. So if you see the angular frequency is a function of the stiffness and the mass, right? So when you could say that the natural frequency is the representation of how the elasticity, the interaction between the elasticity of the objective is interacting with the gravitational pull. Yeah, you could say that. As you look at this expression, 12 and 13, especially 11 and 12, yeah, for sure, because it's the interaction between the stiffness, not necessarily the elasticity, but you're talking of the stiffness, the gravitational pull. Of course, the gravitational pull is directly related to the wave. So you might be true. I don't know whether you wanted to understand in detail or what, but your statement makes sense. But don't forget that not only the two quantities, we also have the weight. So with that, we have obtained the period. So the reciprocal, of course, of the period is what we call the natural frequency. Sorry, the reciprocal of the, 1 over t is equals to f. That is from physics. So that's why we are saying the reciprocal of 17 is the frequency, the natural frequency. Remember omega, the small letter omega, the small omega. Remember the cap omega is like this. The small omega, this is what we refer to as the natural, the angular frequency, okay, rads per second. And then this f is what you call the natural frequency, and the units are cycles per second or hertz. And it's a reciprocal. So of course we say f is equals to 1 over period. This is what we are having here. Okay. So this is just rearranging the equation 17. Now you remember from trigonometry, I don't know whether at this stage I should give you this. So you're looking at equation 16. So from trigonometry, this is in your SMP. We know that if you're given something like sine A plus B, this is given as sine A cos B plus cos A sine B. So this will be sine A cos B plus cos A sine B. This is in SMP, so no worry. So it means we can write this equation in a more compact way. At the same time, there's also another expression that will become in handy from complex number to trigonometric function. So we say, if this is J A, this can be written E raised to J A, where J is a complex. This is like the square root of -1. I'm avoiding to use I because there's somewhere else we are going to use it. So we say this can be written as cos A plus J sine A. So again, these are just identities or expressions. They are in your SMP, or they are in your, they should also be in your system. When you see them there somewhere, they help to simplify your work. So that's why we are saying, using the identity from trigonometry, we are saying equation 16 can be expressed as given in either of these two equations. Okay. So we have expressed it in complex form. Let me take it back here. So we are saying sin A plus B, sin A, sin B, sin A cos B plus cos A, sin B. So you are saying here we are written U naught cos omega t plus V naught of omega sin omega t. So what have happened here is that there has been an introduction of, here is that, here is this. Then we'll be left with this expression here. So you're saying using this identity, we've been able to compress, but we have introduced other quantities, the alpha and beta, because if you look at the expression in equation 16, we didn't have the component, this component here. We didn't have the alpha, we didn't have the beta. We just had the, where we had the omega t. You look at this expression, you only had the omega t here. So it's like we are introducing here, in front here we are saying sine alpha t, and then you can assume alpha is 0. And then here we are saying cos alpha t, then you assume alpha is 0. So that they can, I mean, not necessarily 0, it can be 1. So that our expression does not change. It's like you are multiplying this part with, it's like you are multiplying this part with 1. So like we are introducing here sine alpha t, where alpha is equals to 1, because we know sine of alpha not 1 actually. We are talking of 0 or 90s. We want a condition whereby sine alpha t will either be 1 in either case. Cos will be 1 and sine will be 1, so that this, it doesn't affect our expression. But now we use that case to use it to compress our expression in this manner. Okay. Where C now, of course, this value C here is given by this expression. Tan alpha is given by this expression, and beta is given by this expression. So in this case, what you are just required to do is just to bring in the issue of alpha, and at least the alpha and the betas are already defined. So you're saying if we assume the alphas are this and the betas are this, then we introduce them to our expression 16. We can be able to express it in a condensed format as shown here. So this one should not worry you too much. Because already, even if you don't want to go into detail about that in the text, you can. But already here, you have given you in equation 21 to 23 what C, alpha, and beta are. Okay? And then that helps us to reduce our expression. So we are still working down towards our motion, the solution of our motion, and then we want to get the different parameters that are required to express our wave. Okay, and we see this is sinusoidal function, equation 20 or 19. C will be the amplitude. Okay, then the betas or the alphas will be the phase angles. Okay, the omega t now, this one gives us the period, of course, we know it's a 2 pi. And then omega is the angular frequency. Such that when we come to this slide here, from equation 19 to 23, you're saying C is the amplitude of the motion, alpha or beta is the phase angle, and our solution of the motion for the simple oscillation. Remember the simple oscillator, where we started with the rigid frame. We started with the rigid frame, single story. Then we express it as using a simple dynamic model. This way, calling it a simple oscillator. It's going 2 and 4. It's even like a pendulum, 2 and 4, 2 and 4. So this motion of our structure of our system, we have expressed it in this form, equation 5, and the solution of that equation is this motion. We are saying because of the applied external force and the damping that is known and the stiffness that is known already of the column, at any one point, we can be able to describe the motion or the position of our structure using this solution. This is the solution. Because it will be varying at different times. We have the amplitude. So as time t is equal to maybe 3 seconds, if it's here, we can be able to say this will be the displacement. Yes? Sorry, I'm having a little bit of sour throat there. All right, sorry. The question that you're asking, what's happening to the structure in discussion? Is it getting hit, vibrated, or pushed or pulled? Or the beam is moving in 1 6 course? Yeah. Yes, this is the structure we are starting with. Our structure here is pulled. Okay? This is pulled and then released. Remember, don't get confused here. We are talking of free vibration. Then you may wonder, why do we have this external force here? So we want to get the initial displacement U naught. So we are going to assess our motion immediately we release. Not the time of application of this load, but we are saying this force here is just to initiate our motion. So our motion, yeah, it could be the way you are saying, it could be displaced, it could be pushed. But we are starting with, based on this condition, the initial condition here, we are saying the initial condition, T is equal to, at T is equal to 0, U is equal to U naught, and the velocity is equal to V naught. So it's like the case here we are saying, the displacement, there is an initial displacement U naught, and the initial velocity. Immediately we reach our structure, there is that initial velocity. It could be 0, it could be 10, but this force should not confuse you when we come to analysis of force vibration. For the force vibration, it means our motion, this force itself, the application of the load is taken into consideration during the analysis of our motion. That is, if it's a force that has to stay in place, pushing and pulling throughout, pushing and pulling, or if it's an impact load, we have to consider the time at which it's applied. Yeah, remember this kind of forces we are talking here. The impulse, we will have to consider this small time duration that the load is applied so that we can analyze the externally applied force. But for the free vibration, what we are just interested in is the initial displacement. Yeah, so your question is right, Levi. The way you're saying it could be, let's say it's not being hit, so that we do not preempt ourselves with the impulse load, but we could say it was pushed or pulled initially and then released. And from that point, no other force, external force was applied. So the motion continued without external gravitation for it to be free vibration. And again, we said there is no damping. What does that mean? Our motion continues indefinitely. And this can be seen in the solution. Our solution is in form of a wave like this. And as you can see, the amplitude does not change. The amplitude does not change. So it means our motion may continue until I don't know when. If there's no damping, it will continue like that. We are going to see cases where there is damping. When we come to the second amplitude, this is the initial amplitude. Let's say this is A1 or C1, because we are using C. So for damping, we continue dying out like that until the end. Finally, our motion comes to a stop. Our structure rests or gets back to initial condition if there was damping. So this is the case when there is no damping. Okay, and this is the solution. And this is what you call the response. How did our structure respond to the applied? How does it respond to the applied load or applied initial displacement dynamically? Our dynamic response. When you are told to analyze the dynamic response and you are given condition, this is the type of solution that you are going to get. It's not just an exact or just one value, unless I tell you at this time. At time t is equal to 10 seconds. Of course, now that one we can come exactly at that point, and we can be able to say the displacement for our structure is this value. Okay. right? And to understand what I mean, if this was your structure like this, it means your structure from the initial displacement, it was displaced like this. Okay? And then we are saying this was the initial displacement, u naught. And there's the initial velocity, u dot naught, or v naught. Okay? And if there's no damping, it will continue moving to and fro. So it will continue going to and fro, to and fro, to and fro. So if we say at 10 seconds, if it will have been at this position, if at 10 seconds it's at this location, so this is the displacement that you are going to obtain. Okay. Not the total maximum that is occurring, but at least 10 seconds. If you're given a 10 seconds, from this wave, the wave that you are given here, you just come and read off at 10 seconds what is the displacement. So you may wonder why in the previous slide we introduced the alphas and the betas. It's because we know for this kind of a motion, for a wave, we are going to have the phase angle and also the period. Okay, so that's why we introduced the T's, that's why we introduced the alphas here, so that now you can see what we are talking of, the phase angle. And we might talk of two motion being in or out of phase. And you can see the angular, this differentiation, the differentiation of first derivative of this motion, you know, this is like the gradient you are obtaining here. That's why it's given as V naught. The initial velocity is the displacement. Yeah. Okay. Then, all right. Good. It's a phone call that is really disturbing me. I don't know what to do. Okay. It's good. I hope now you are appreciating a few facts here and there that you are deriving. So as always, as I say, I find it necessary or important that we go through things. They might not be so much. We are in applied sciences, engineering, but again, I say it's good to understand the basics. It's good to understand the foundations where we are coming from. That's why we write this kind of derivation to understand. Instead of just coming to give you the equation here, I give you the equation 5, then I tell you the typical solution, then I move you directly to the solution here. Then I show you this graph. It's good you see how that motion occurs or how we derive that. And that's it. As simple as ABC. Yeah. So just do some little bit of practice, a little bit of refreshing on ODE, and some characteristic features of a wave, and you are good to go. Application of this equation is very easy, as you're going to see with just one or two examples before we can call it off for today. If you look at example 1, we have a simple example here. So we are saying there is a weight that is suspended. So you have a weight that is suspended vertically using a spring. So this is a spring. Okay. And the spring stiffness K is given, and you are told to determine the natural frequency of the free vibration of this weight. The weight is given as 15 Newton. So if you're told to get the natural frequency, and you're not told the angular or circular, to be on the safe side, obtain the natural linear frequency. Okay. So, of course, you just need to use the equation. The equation, I think, we derived it in equation 18. That's the equation you are using. So the expression will be given by, will be determined by what you have. You have the stiffness, you have the weight. Of course, from the weight, you can get the mass. So on and so forth, we can be able to get what is F. We just need to substitute, plug in those values. We have the K, the M, and of course, we know mg is equals to weight because we are given the weight. So m is equals to weight over g. And this is what now I see here. You multiply by that, you get 5.76 half. Okay. Very simple. Again, you look at another little bit. The first one was very basic. Let's see at a little bit advanced one. It's not complex, but now we have added a little bit more of information. And also it looks more of an actual scenario that you may encounter, because the first one is just talked of a spring. So maybe that's just for demonstration purposes, but let's look at a structural case. So you are required to calculate the natural frequency of the frame shown in figure below. And you also to calculate the natural period of the vibration. Here, in this case, you are given the initial displacement. So U naught is 25, V naught is 25 millimeters per second. Now, this is the second part of the question. So the first part, we are supposed to calculate the angular frequency, the natural period. Now, the second part is that if the initial displacement is given and the initial velocity is given, you have to calculate the amplitude and displacement at time t is equals to 1 second. So in this case, now you can get the exact value because you already told at what time. So what it means is that you get the equation of motion, then the solution, and the solution will be in wave form. Then because you are given time, you plug in those time values, you'll be able to think that. And you are given the fractional rigidity of our column, of our beam. Is it? Is it? Yeah. Is 30 times 10 to the power 12. So this is the structure. Of course, if you look at this, the lengths are different. This is 1 meter. This is 0.8 of a meter. And then the mass is given. The columns, they are massless, as we said. And the columns, their work is to provide the stiffness. So you have the stiffness of the column KAB and the stiffness of column KD. And we need to first get the equivalent stiffness because for our body, we always, you may have a frame structure like this, no matter how many photos you are considering. Okay. Yeah. But our dynamic system will be represented using a single stiffness like that. So how many levels? So you have the mass at this level, the mass at this level, this, and all that. Yeah? So we need to get this equivalent stiffness at each of the 4 levels. So the stiffness of this and this. Okay. So before we solve this, it's good you note a few of no, this is direct already. I think we have given that. You're saying this is like 2 springs. It's like a spring. This is a spring in parallel, and then another one here. And then we are saying the equivalent spring stiffness is KEAB plus KCD, so that we will end up having just one equivalent spring stiffness and lumped mass at this point. Okay. Now, again, now we are talking of real columns. Yeah? So you have to look at the fixity. This is fixed. This head will kind of be will be fixed and it will behave like Zeta and Aurora. And I believe this one I might have given them in this space because this is 12, 12 EI over R cubed. I want to explain using this slide. I have gone ahead and some few slides. These are just some notes to refresh your memory because you already know that. We are looking at some notes on the spring constant, equivalent spring constant. Of course, you remember that F is equal to KP from the equation of motion, from the, Hooke's law. So K is equal to F of a displacement. So that's where it's an initial starting point of the stiffness for columns. So example of different spring constant, these are the columns. I have positioned them in an inclined position. So you can read them in either direction. So in this case, we are saying if this is fixed, and this is a cantilevered column, so the spring stiffness is given by 3 EI over L cubed. Now, if this is fixed, this is Aurora, you have 12 EI over L cubed. Now, if this is pinned, this is Aurora, it's the same almost like the cantilever. And you give an example here. This is fixed, this is pinned. So if this is fixed, now this is rigid. So this being rigid, meaning there's no deformation at all. So our motion, this is fixed, so this is like this. Then our structure does not deform. Then this one is like this. Okay. Remember here there is the rotation, here there is no rotation because of the fixity. So in this case, when you look at these, because of the rigidity of the column, doesn't of the beam doesn't deform this deck, it means if you look at this top part, it's kind of just sliding. The column is just sliding. It's like the same case where if you could have rollers, and then the column head, the column curve is just sliding on top. So like you have fixed roller, pin, roller. Okay, and that's why you have fixed roller, 12 EI per L cubed, and then you have pinned roller, 3 EI over L cubed. And in our case here, why I came to this slide is so that you can understand this question. This is fixed roller because our assumption is that the beam is rigid. Okay, so it's fixed roller, fixed roller. And so you have 12 EI upper L cubed, 12 EI upper L cubed. I hope you understand that. And then you just need to plug in your values that you are given. You get what is the equivalent stiffness. From there, it's very easy. Just the first question was, what is the natural angular frequency? Omega, K, and here we just put E so that you know you're talking of the equivalent spin constant or stiffness, kg over omega. You substitute that, rads per second. Okay. Then the other question was natural period. So T, we know F is equal to omega over 2 pi, right? So you just need to plug, the omega is calculated, whatever you get it in cycles per second. Natural period, T is the reciprocal of the natural frequency, like that. And then, that's the first part is finished. The second part is when now we are to calculate. If you are given the initial quotation, so you want to know what is the amplitude and the displacement at time t is equal to 1 second. So in this case, we derived the equation. We derived this. Now, it depends with what you are given, what you know, and what you are given. You know that what equation you need to use. Okay? Because if you look at this expression, you have equation 19, equation 20. And in equation 20, we know what is C, what is alpha, what is beta. If you use any other equation, maybe we may have some unknowns at the mid. So in our case, I opted to use equation 20 of the cos U, because there's a displacement that you need to get. U is A cos omega t minus beta. So what I need to obtain is the value A. And at time t is equal to 0 second, you are already given the initial displacement, 25, and the initial velocity, 25 meters per second. So from equation now 21 to 23, I can get what is A. I can get what is beta. And remember when you are punching the trigonometric, these functions, the sines and the cosines, the calculator have to be set in radians. Because the value of omega that you're going to put there is in rad. Otherwise, you may get different values. Yeah. Okay. But this is the particular case for this when you have this tan or cos or sine, and then you're working with values inside there. Otherwise, in other terms, then that is just be in that decrease. So once you get what is A and B, so your equation is like this, and at 1 second, you just need to put T is equals to 1. You get that the displacement is 24.2 millimeter. So what does that mean? That means our structure was displaced. Let's say it was displaced like that. Yeah, that's the initial displacement. So at 1 second, I don't know how the motion is. So this is the initial displacement, which was 25. So after 1 second, it have gone back. Assume it have not completed our cycle. So at 1 second, it have gone back. Therefore, the displacement of our structure is 24.2. It could go 2 and 4, 2 and 4. And also you can try, I also tried using, let me see whether I can show you that. I tried using I cannot escape. Okay, seems I cannot escape. But I also tried using the other equation. Instead of using the u is equals to cos, I used the sine one, and I was able to obtain the same equation. I wanted to show you the working because it's why you are seeing this highlight. There's an extension in my PowerPoint here on this head here. I was working now with the sine, and I substituted the values for the same. So it's as simple as that. Application is very easy. Derivation might have taken a toll on you, but once you just do a little bit of practice, you'll find it's very easy and enjoyable to work that out. Already I have mentioned about the different spin stiffnesses. Let's stop there for today. I've given you for a few examples that you can look at. And from our main reference, the Mario Powers book, there are a few examples you can look into. That's very easy. Look at this example, see what you can obtain. This is not solved anywhere, so don't say that I have to go here. It's not solved anywhere, but as easy as it seems. Next time, we're going to start on when there is stamping. So allow me to stop there for today and to take any question if somebody has, whether here, whether in live question or question welcome. So that's the end of our class for today. Any question, they are welcome to ask. But if not, then we can stop there for today. Don't wait until the end of the semester to revise. It's always good to be alert always. And that's it. So I'll be waiting for anyone with a question or even here on the chat section. But if not, we stop there for today. And let's say thank you for your attendance. Okay, that's all for today. Enjoy your rest of the day. Thank you. I'll stop the streaming now.